Okay, welcome to the last session of the workshop. The first talk is given by Daniel Kane on AK testing of distributions.
Hey everybody, welcome. So yeah, I'm going to be talking about AK testing of distributions. And well, what is distribution testing? Well, at a very high level, you're given samples from a distribution D, and you want to determine whether or not it has a property P. I mean, this is pretty old. It goes back at least to Pearson in the 19th century. It's been known in statistics as hypothesis testing, and it's one of the most basic questions. And it's been sort of studied in theoretical computer science for about 20 years, sort of as a, another version of, graph testing and function property testing and things like that. You can test distributions as well. What are the basic properties that you want to test for? Well, the first one is uniformity testing. Is P the uniform distribution over its domain? Slight generalization is identity testing. I give you some explicit distribution Q and ask, is P equal to Q or not? If Q is the uniform distribution, this is just uniformity testing, but this is a generalization. And finally, there's closeness testing, where you're given two distributions P and Q, but you only have samples from both of them, and you want to know whether or not they're the same. And well, there's an issue, which is that, as I've stated, these problems, they are not possible to solve in a finite number of samples, basically because you can't distinguish between a coin being fair and a coin being arbitrarily close, but not quite equal to being fair. With a bounded number of samples. So in order to make these possible at all, we need to introduce some kind of separation in the no case. And so the standard way that this gets phrased is that you're given samples from P, and you are guaranteed that either your distribution P exactly satisfies this property that you're interested in, or it is epsilon far in total variation distance from any other distribution that satisfies that property. And you want to distinguish these, and you want to do so with probability of error at most a third. And so, well, the question that we can now ask ourselves is this problem solvable? And fortunately, the answer is now that, yeah, at least under some circumstances, we can solve this. For example, if P is known to be a distribution on a discrete set of size n, then with only O of n over epsilon squared samples, you can learn P. You can find some P hat that is epsilon over 2 close to P in total variation distance. And then you know if P hat is epsilon close to some distribution satisfying your property, the answer must have been yes. It can't be that the real P is epsilon far, and otherwise the answer is no. And so we have an algorithm that actually works. And the question is that this is sort of a linear algorithm that tests by learning. Can you do better than this? And often, yes, you can. And so the basic thing that you can do for uniformity testing is testing sort of based on looking for collisions. So the uniform distribution is the single distribution where it is least likely that two IID samples will be the same. And it turns out that you can distinguish the uniform distribution from other distributions that are far from uniform by just seeing how many samples do I need to take from the distribution before I find my first collision. And how many samples is that? Well, the birthday problem says you need about square root n samples before you see a collision. And it turns out you can get testers that use this sample complexity. Now, if we want to do this in a little bit more detail, so one nice way to formalize this is that it turns out, given samples from two distributions P and Q, it is not hard to estimate the squared L2 norm between them. Now, ideally, if you're looking at total variation distance, you'd like to estimate, the L1 distance from uniform, but that turns out to be quite hard, basically because these absolute values of Pi minus Qi are hard to approximate. Whereas with L2, Pi minus Qi squared is a polynomial in the entries. That makes it easy to get an unbiased estimator. And if you compute the variance, you can estimate them to error roughly L2 norm of P plus L2 norm of Q divided by M, if you take M samples. And so if you want to do uniformity testing, if you can estimate the squared L2 distance between P and the uniform distribution to error about epsilon over n, that's enough to tell whether P is uniform versus epsilon far in total variation distance. Now, the L2 norm of the uniform distribution is not too big. It's only 1 in square root n. So if you plug all of this into the sample complexity bounds up here, you find out that you need m to be about square root n over epsilon squared in order for this to work. And this is actually known to be optimal. In fact, Paninsky came up with a tester with the same sample complexity back in 2003. And so this works. So that's what happens if you want to test for uniformity. What if you want to do general identity testing? So you're trying to test if you're equal to Q for some possible non-identity distribution Q. Well, if Q has L2 norm 1 in root n, or O of 1 in root n, then the same algorithm works. If it doesn't, if it's got some heavy bins, it turns out you can reduce to this case. There's a way to like split up the heavy bins, and that makes it have small L2 norm, and you run the L2 tester. And in fact, with a little bit more work, you can just black box have a reduction between identity testing and uniformity testing. I will say that these works were not the first to get that. It was originally proved by Valiant and Valiant in 14. And furthermore, if Q is far from the uniform, if it's not one of these sort of evenly-ish distributed across all bins, you can often do better. Roughly, you need the 2/3 norm of Q over epsilon squared samples, but can do actually slightly better than that in weird cases. But yeah, that's more detail than I want to talk about. The final basic problem is closeness testing. It turns out here you need some more samples. You need roughly n to the 2/3 over epsilon to the 4/3 extra samples if epsilon is large. And one way of achieving this is there's a way of sort of by taking k samples, you can reduce to the case where the L2 norms of P and Q are 1 in root k, roughly, and then using the L2 tester. And I don't want to get into too many of the details of this. This is not what this talk is supposed to be about, but that's one way to do it. Okay, so these are all nice results that are optimal if you're looking at P being an arbitrary distribution over a domain of size n. But in practice, lots of distributions that we might see won't be over finite domains. Like you might look at distributions over like people's weight or height or income, which are domains that are either infinite or really, really large. And the question is, if we're trying to do things for distributions on an infinite domain, can we solve these problems? And unfortunately, the answer is no. These problems very quickly become impossible. And this shouldn't surprise us because we had these tight upper and lower bounds that went to infinity with the domain size. And well, for example, if you want to distinguish between, do uniformity testing over the interval 0, 1, it's not possible in a finite number of samples to distinguish between the uniform distribution over 0, 1 and the uniform distribution over a large random subset of 0, 1. Because until you have enough samples that you start seeing collisions in the latter case, it's just going to look like you have a bunch of IID samples, and there's sort of nothing useful that you can say. And so where does this leave us? If we're actually looking at distributions over an infinite set, can we just not hope to solve even basic distribution testing problems? Well, maybe we can if we have a way to rule out these degenerate examples. I mean, you don't expect that people's distributions over weight will be like some discrete distribution over some weird random subset. You expect that it's going to be some kind of continuous thing. And so what you're going to do is you're going to assume that your distribution P satisfies some niceness condition. Maybe it's log concave, or it's a mixture of Gaussians, or it's Lipschitz with some parameters, or it's a piecewise polynomial, or you could go on and on and on listing out, assumptions that might be reasonable. And well, the question is, if I make these assumptions, and critically assumptions that rule out the degenerate bad cases on the previous slide where you've got a distribution over a random subset, then is it now possible under these distributional assumptions to solve our original testing problems. Unfortunately, when you phrase it this way, it sounds like it might be a huge mess, because there are a whole bunch of different conditions that you might want to try applying, and in theory, each of these conditions will lead to a different tailor-made algorithm for doing property testing, and that would really not be very helpful. I mean, it'd be really helpful if you want to churn out a whole bunch of papers, but it's not useful for having a good theory. So what we really want is we want a unified way of treating all of these different conditions. And for that, we need to know, what do these conditions have in common? They've got, maybe it's that they have some kind of continuity assumptions. And if we want to do that, we need a way of quantifying sort of how continuous are we assuming P to be. Or maybe another way to look at it is, the problem with these degenerate examples are that, like, there are a whole bunch of different values where you can sort of independently set the probability mass of P on those values to be whatever we want. And you end up with these weird functions with lots and lots of oscillations. Maybe there's some way of bounding the oscillations. And unfortunately, I don't have a great way of motivating this, but to sort of satisfy these criteria, what we really, it turns out, we need a better notion of measuring distance. And so total variation distance, one way of defining it is the supremum over all sets S of the difference between the probabilities that the two distributions assign to that set S. And the problem with this notion of distance is that it says that the uniform distribution over a large random subset is really, really far from the uniform distribution over 0, 1, because you can just take S to be exactly that set. And the problem is that this notion of distance is too powerful. It can detect these stupid things that oscillate a bunch of times and note that they're very, very different. So we're going to define a new notion of distance. So let P and Q be two distributions on the real line, and let K be a positive integer. We define the AK distance between P and Q to be the supremum of the difference between the probabilities that P and Q assign to S over all sets S that are a union of at most K intervals. And this is critical. It means that this uniform distribution over a large random subset, it'll actually be very close in AK distance to the uniform distribution over 0, 1. Because even though they're very far in total variation distance, over any interval, it's very likely that they'll assign nearly the same probability. One more note about this definition, there's sort of an equivalent notion, which is technically how it's usually defined, which is that if you look at those K intervals, it partitions the real line into something like 2K plus 1 intervals. And then what you can do is you can think about, like, looking at the distribution, like, P and Q each give you a distribution over these intervals in the partition. And then you can look at sort of the total variation distance of those sort of restricted distributions. And this is another useful way of thinking about it that I will be getting back to later. Okay, so we have this AK distance. What can we say about it? Well, when K is 1 or K is small, this is sort of like the Kolmogorov distance, the maximum difference between the probability density function, cumulative density functions of the two distributions. Secondly, it's clear that the AK distance is always at most the total variation distance, because the total variation distance lets you use any set, and this only lets you use some. But for nice distributions P and Q, the AK distance should approach the total variation distance as K approaches infinity. And we can start using more and more complicated sets to distinguish them. And in fact, if P and Q both satisfy one of our niceness conditions, it ought to be the case that we can pick a K that's large enough such that the total variation distance and the AK distance will differ by at most epsilon. And so how do we prove that? Well, the first key observation is that if the difference of the probability densities of P and Q changes signs at most 2K times, then the total variation distance equals the AK distance. Now, why is that? We've got these distributions. They only change sign a small number of times. Now, what is the optimal set for distinguishing P from Q? Well, it's just the set of points where the probability density of P is bigger than the probability density of Q. And that's just a bunch of intervals sort of between every other pair of sign changes. And so if there are only 2 K sign changes, this is a union of only K intervals, and it works. We get equality. So when now is this condition going to be satisfied? Well, let's suppose that P and Q are both T piecewise degree D polynomials. So you can split the real line into T pieces, and on each piece, P is a degree D polynomial, and similarly for Q. Then if we take K to be T times D plus 1, total variation distance equals AK distance. And what's the point? I mean, the point is, if you sort of take the union of the partitions, the common refinement, then you've got a partition of the real line where on each part, both P and Q are degree D polynomials, or their densities are, and 2 degree D polynomials cross in only D points. And so we've got a bound in the number of points, and we apply the lemma. Okay, so that much is good, but most of the families that we're looking at are not just piecewise polynomial distributions. So what can we do if we want to look at like log concaves or something? Well, the corollary is that if both P and Q come from distributions where they can be epsilon over 4 approximated by T piecewise degree D polynomials, then the total variation distance and AK distance for the appropriate value of K differ by at most epsilon. And the proof is basically you replace P by P prime and Q by Q prime that are in these classes. The total variation distance between P prime and Q prime is their AK distance. And you just need to do the triangle inequality a bunch of times to translate back and forth. And every time you do it, you lose some factors of epsilon over 4. And so this is the result. And then if you look at this in applications, for basically every family that you care about, there is some usually fairly reasonable value of K for which this can work. So if your families are T histograms, I mean, that is just a piecewise degree 0 polynomial. Log concave distributions can be approximated by piecewise linear polynomials with pretty good error. Mixtures of Gaussians, well, a Gaussian you can sort of Taylor expand it about the middle, and you can approximate by a log 1 over epsilon degree polynomial, and then you just need to sum those up. Lipschitz functions you can approximate by piecewise constant functions. T-modal distributions can be approximated by piecewise constant. And so for each of these families, you can find a value of K such that 2 things in the family, the TV distance and AK distance, differ by at most epsilon. So what do we gain from this? Well, for one thing, I mean, AK distance is somehow, it's not nearly as strong as total variation distance. It makes a lot of things easier. For example, it's not hard to show that you can learn very effectively with respect to AK distance. So given only K over epsilon squared samples from a distribution P, you can learn it to epsilon error in AK distance. And note that to do this with total variation distance, you need N. You need the domain size, which is infinity. This is not possible in total variation distance. And the proof of this is quite easy. This just follows from the VC inequality, basically because your test sets are just unions of K intervals, and that has VC dimension O of K. And once you have this, I mean, it allows you to do, for example, learning of structured distributions. If you know that P comes from some family where AK distance approximates total variation distance, then you can learn some P hat, which is close in AK distance, and then find the closest element to P hat that's in your family. And then you found another distribution in your family that is close in AK distance to the original, but since your family AK distance approximates total variation distance, you've learned in total variation distance. Okay, so that's for learning. What if we want to do testing? How do we take advantage of AK distance approximating TV distance for testing? And the way we're going to do it is we're just going to replace testing by AK testing. Given K and samples from P, we want to distinguish between P satisfies our property of interest or is epsilon far in AK distance from any distribution satisfying the property. So the only difference here is that the sort of soundness case, we want the distance to be large in a k distance. And so the point is that if we can do this, then we could solve structured testing. Because if P and Q lie in a class C where AK distance approximates TV distance, then the real problem we want to solve is we want to distinguish between either P equals Q or the total variation distance is large. But that's sort of if and only if either P equals Q or the AK distance is large. And so if we can solve AK testing, we can distinguish these latter cases, which allows us to solve the former. So if we can solve AK testing to error epsilon over 2, then we can solve the structured testing problem with error epsilon. So the only question is can we solve these AK testing problems? And well, yeah, we can. So this result is from 2015. There is an algorithm that performs AK testing with constant probability of error using square root k over epsilon squared samples. And a few things I'd like to note. One, this gives us square root n over epsilon squared for identity testing for discrete distributions over a domain of size n, because for distributions with domain size n, AK testing is the same as normal testing with k equal to n. I mean, AK distance is equal to your total variation distance. The second thing I want to note is that this sounds like it's not too different from that discrete distribution testing. Remember, AK distance is sort of the total variation distance once you've picked the optimal partition into intervals. And so somehow, if you knew what that optimal partition into intervals was to distinguish P and Q, then it literally would just be testing, identity testing of two discrete distributions over these 2k intervals. The difficulty is, what do we do if we don't know that partition? The final thing I want to note is that this, as a black box now, gives us testers for identity testing of Lipschitz or log concave or mixture of Gaussians or T-modal distributions or whatever. And for all of these cases, it gives you near optimal testers. And so this gives us a nice unified theory for structured distribution testing, where for almost all of these natural structures, this single tester gives you basically the right answer. You just need to pick the right value of k. Okay, so before I get into the proof of this, I want to quickly make a note that for AK testing, uniformity testing and identity testing are basically the same thing. And this is because AK testing AK distance is invariant under monotone reparameterizations of the interval. Sort of the only thing that AK distance cares about is what it means for something to be a union of k intervals. And so if you stretch your x-axis out, AK distance stays the same. And in particular, if you reparameterize using the cumulative density function of Q, you can assume that Q is just the uniform distribution over 0, 1. And so we're going to do that. Okay, so what's the intuition? We know that there are some 2k intervals that capture a total of epsilon discrepancy between P and Q, at least in the soundness case. This is what we're trying to see if it exists. Now, suppose that these are roughly evenly spaced. I mean, these intervals are clearly not exactly evenly spaced, but it's sort of good enough. Then if we partition 0, 1 sort of obliviously into O of k intervals, it's not going to capture all of the discrepancy, but it's going to capture a reasonable amount of the discrepancy. There's like a reasonable number of these intervals where like the difference between P and Q on this interval is actually reasonably big. And if we're just trying to detect for this particular partition that there's a reasonable amount of discrepancy captured, I mean, that's just a testing for discrete distributions. You need square root k over epsilon squared samples. Done. Unfortunately, this doesn't always work, because it could be that even though there's a small number of intervals that have a big discrepancy, these discrepancies all cancel out over this partition. It could be that for like each bit in this partition, P is bigger than Q on the second half of the interval and smaller than Q on the first half of the interval. And over these intervals, everything cancels. Now, for this version, it's easy to deal with. We can just use twice as many intervals, And now we've suddenly captured all the discrepancy using 2k intervals. And so we need like square root 2k over epsilon squared samples. Of course, this just begs the question, what happens now if these things cancel over these smaller intervals? Well, we can keep going. We can split into more and more and more intervals. But the problem is if we split into 2 to the t times k intervals, we now need like square root of 2 to the t k over epsilon squared samples, which is too many. But there is something that saves us. If we pick t to be the right value, then the discrepancy, this thing does capture epsilon discrepancy between p and q, but it captures it on only only k of these 2 to the t times k intervals. And if it's the case that k of these intervals of mass 1 and 2 to the t times k, it contribute to these epsilon error. Well, if instead of just doing a standard uniformity tester, we go back and look into the details of this L2 tester, the squared L2 distance between p and q is at least epsilon squared over k, whereas the L2 norm of the uniform distribution is like 1 in square root of 2 to the t times k. And so the number of samples that we need, roughly, is the ratio of these is roughly, k over square root k over epsilon squared divided by 2 to the t over 2. And somehow the fact that we've had to split into more intervals is actually better for us if the size of the signal that we're detecting is really supported only on k of them anyway. Now, this intuition, by itself isn't really a proof, because I sort of had to assume that all of my discrepancy was located on intervals of just a given scale that I could then detect with this partition of that particular scale. But it turns out that there always is a scale that you can use. So the lemma is that if you have any p where the AK distance between p and uniform is at least epsilon, there is some positive integer t such that if you partition 0, 1 into 2 to the t times k equal intervals, then the squared L2 error between p on that partition and the uniform distribution on that partition is bigger than, say, epsilon squared over k divided by 2 to the minus t over 4, say. And if we have this, this gives a really simple algorithm. I run an L2 tester for each value of t. And even though the squared L2 error that I'm trying to detect gets smaller and smaller, the L2 size of the uniform distribution also is getting smaller even faster. And it turns out that my sample complexity here is actually getting smaller with t rather than bigger. And so I can easily, the t test requires root k over epsilon squared divided by 2 to the t over 4 samples. I can just run each test in parallel with root k over epsilon squared samples. If p is equal to q, it will pass every one of these tests. If p is far from q in AK distance, it is guaranteed to fail at least one, or with high probability. And so this allows me to distinguish. Okay, so that is identity testing for AK. But now if we want to do structured closeness testing, we should figure out how to do AK closeness testing. And to get an idea of what we need for the sample complexity here, and sorry about this thing, let's take a look at some of the things that we've seen. So for learning, over a discrete distribution of size n, we need n over epsilon squared samples. Over AK, we need k over epsilon squared. For uniformity or identity testing, over n, we need root n over epsilon squared. For AK, we need root k over epsilon squared. For closeness testing over discrete domains, we need whatever plus n to the 2/3 over epsilon to the 4/3. So for AK closeness testing, we obviously need k to the 4/5 over epsilon to the 6/5 samples. I hope everyone guessed that. No, but I mean, somehow for learning and uniformity testing, you get the same sample complexity that you would get if you knew what the optimal partition was for distinguishing. But somehow when you get to closeness testing, you can't assume that anymore. Somehow it's worse. You actually need to spend more samples to figure out a good enough approximation to that interval. But yeah, so the result is that this is basically sample optimal. You need k to the 4/5 over epsilon to the 6/5 plus root k over epsilon squared. And how do we think about this? Well, the idea for identity testing was you sort of obliviously break the domain into buckets, and how am I doing on time? And you run an L2 tester over those buckets. Now, the problem was that in order to break things into buckets, we wanted to break them into buckets where Q assigned them equal mass. And we can't do that without knowing what Q is. And in fact, because like everything is sort of invariant under scaling the domain, there's not like a natural way to break the domain into pieces if we don't know what scale P and Q are at. And so how do you break things into buckets if you don't know what Q is? Well, in some sense, there's really only one natural way to do it. You take samples from P or from Q, and you use them to break your domain into buckets. You sort of use those as your dividers, and between consecutive samples, those are your buckets. So, I mean, there's almost, in some sense, there's almost only one algorithm that we can use. You take M samples from each of P and Q, you use them to break your R into buckets. You then consider these distributions P and Q sort of over like as distributions over these buckets, as discrete distributions now. And then you use M more samples to run an L2 tester to see if they're the same or far apart. And in total, this requires O of M total samples. And the only thing that we need to do is we need to analyze this final tester. We need to show that with high probability, these buckets capture enough L2 distance between P and Q that this tester that we're running actually can distinguish them when they're far apart. So how do we do that? Well, if the AK distance between P and Q is bigger than epsilon, there are some K intervals that capture total discrepancy of at least epsilon. And if we break it, if we subdivide them a little bit, we can assume basically that each of these intervals has total mass O of 1 in K and captures a discrepancy of at least omega of epsilon in K. So the question then is, if we take now one of these random subdivisions that we get by just sampling from both P and Q and then using those as the breakpoints for our intervals, how much discrepancy is that going to capture? And the lemma is the following. If there's some interval I in the original, in our partition with discrepancy delta and total mass 1 in M, then with probability omega of M times delta, there is a bucket whose left endpoint lies in this interval I and captures a discrepancy of omega of delta. Now, how do we show that? Well, I mean, what I'm going to do is that you've got your interval I. Somewhere to the right of that is whatever the next point that you sampled. And assuming we sampled a point from I, and note that I set this up so we probably didn't sample more than one point from I. There's going to be an interval from that point to the next point, and depending on which point we picked, there's going to be a discrepancy. So P and Q have some probability densities on this interval, and depending on where I pick that point in the interval, I get a discrepancy, and it's some kind of function. Now, what do I know about that function? This interval captures a discrepancy of delta. That means that the difference over the whole interval, the probability assigned to P and the probability assigned to Q, differ by delta. And that tells you that if you look at this discrepancy curve, the difference between its value at the left endpoint of the interval I and the right endpoint of the interval I has to be delta. And in particular, that says that there have to be, since this thing is sort of continuous with respect to the probability densities, there's got to be a reasonable amount of mass in here where the discrepancy is at least, say, delta over 4. And so that means that there's a reasonable probability, in fact, omega of M delta, that we capture a discrepancy of at least delta over 4. Okay, so what's the analysis now? Our optimal partition has K intervals with discrepancy epsilon over K. Each of those has a probability of M epsilon over K of capturing some discrepancy. So we expect that the partition that we find will have M epsilon intervals, each capturing a discrepancy of epsilon over K. And in particular, that means that the squared L2 error between P and Q over this partition that we found should be something like M epsilon cubed over K squared. And the L2 norm over this partition, it's not hard to show, should be about 1 in root m. Because if you do this random partition, each of the bins should be about the same probability mass. And so this means that in order for the tester to work, the number of samples m that you use in the second half needs to be more than 1 in root m divided by m epsilon cubed over k squared. And when you solve for m needs to be at least k to the 4/5 over epsilon to the 6/5. That's just how the algebra works out. So that's the upper bound. If you want to think about the lower bound, well, firstly, there's a weird thing about this tester. It's sort of what I'd call an order-based tester. What it does is it takes a bunch of samples, each from P and from Q, and it remembers which distribution you took which sample from. And it looks at what order the samples came in. It pays attention to like which samples came between which other pairs of samples and things like that. But it doesn't use any other information. There's no notion of distance between samples that we use. There's no notion of, exact location of samples or anything like that. And that's, in some sense, for a good reason. And it's because remember, AK distance is invariant under stretching the domain. There is no meaningful notion of distance between points or absolute location of points. If you just reparameterize the domain, all of these things become sort of irrelevant. And in fact, what you can show is that if you take a domain that is large enough, then sort of without loss of generality, any tester that you use is going to be an order-based tester. Because basically you can always find a subset of the domain on which your tester actually is close to being an order-based tester. And this helps us prove lower bounds. And for this, there's a gadget. For the yes instance, we just have a block of mass where P is equal to Q. And for in the no instance, we have a block of Q and a block of P and a block of Q. And this gadget has two useful properties. Firstly, if in the yes instance, P is equal to Q. In the no instance, they are far from each other, and that distance is totally noticeable by a single interval. On the other hand, they're hard to distinguish in the sense that if you use an order-based tester, there is no way that taking two samples from these distributions will tell you any information whatsoever about which case you are in. Basically, because if you take a sample from P and a sample from Q, in both cases, it's equally likely that P will come first or Q will come first. And that's all an order-based tester could ever tell you. And so this gives us our construction. I'm going to split my domain into m times k buckets. K of those buckets, I'm going to fill with a gadget that has mass epsilon over k. And the other m buckets, I'm going to set P equal to Q and give it mass 1 minus epsilon over m. And these are going to be to add noise, basically. In the yes instance, P is equal to Q. If I use no versions of the gadgets, then P and Q have epsilon difference in AK. But the claim is that these are hard to distinguish. And the point is you can only distinguish them by looking at what happens in these gadgets. But you can only get information from gadgets with at least 3 samples. Because gadgets with 2 samples, the yes and no instances look the same. So the size of the signal that you get is something like k, the number of gadgets, times m epsilon over k cubed, the probability that that gadget has 3 samples. On the other hand, these heavy bins provide noise. There are m heavy bins, and basically each bin is reasonably likely to have any constant number of samples coming in them in any combination. So for any combination of 3 P's and Q's that you might see, these heavy bins are going to provide m plus or minus square root m many copies of that pattern. And the plus or minus square root m is basically adding noise here. And so in order to be able to distinguish the yes case from the no case, you need the signal size to be bigger than the noise size, and then you do some algebra, and you get m is bigger than k to the 4/5 over epsilon to the 6/5. And am I almost out of time? Okay, so I'll quickly talk about one interesting thing here, which is the domain size. In order to get this lower bound, we needed to do this Ramsey theory-based reduction to order-based testers. That requires a really big domain size. And so the question is, how big a domain size do you actually need? And I'm not going to go into too much detail, but basically you want a construction where your gadgets are such that you can't learn any information from the location of the points, only the orders help. And there is a way by sort of applying random affine transformations to make that happen, as long as the domain size is at least exponential in K. And this is a little weird, but it turns out it's actually necessary. There is a tester where the sample complexity is K to the 2/3 over epsilon to the 4/3, the thing we would have suspected given the finite domain case, times a polylog n over K. So until the domain size becomes exponential, it does behave sort of similarly to the discrete case. So in summary, basically all of these structured 1D distribution testings can be solved nearly optimally with AK testing. We've got some bounds on what the things are. And for future work, there are some problems still to solve. One of them is the exact domain dependence for the closeness testers. We don't really know. We know that there's a log n over K, but the power of that log is still, there's a mismatch between the known upper and lower bounds. It's also an interesting problem to try and find new applications of this. I mean, there are all sorts of structured testing problems that we might care about. It's interesting to see what they would do. And the big and difficult thing that's still pretty wide open is to try and generalize this theory to functions in D dimensions. So this does a really good job of solving structured testing problems for families of functions on the line. But even coming up with the right notion of AK distance for functions on RD seems to be pretty hard. And then once you have it, finding the right testers is again somewhat difficult. And so there are some recent sort of partial results along these lines, but getting a full theory that works is still, I think, a ways away. Okay, I have some other slides, but no time to get into them, and this seems like a good place to stop. So, any questions?
I mean, you said that D dimensions is hard, but if D is equal to 2, could that simplify things? Because if you were to do just like packing with rectangles or something, I mean, like there the VC dimension is constant, and then would many of these things carry through?
So what happens even when D is equal to 2? Well, I mean, I think a lot of the problems come up even when D equals 2. I mean, one of the main problems is just how do you generalize AK distance? And the point is that, like, yeah, so the work that has been done has been like packings with rectangles, but do rectangles actually really capture the distributions that we want? Like, what if what you're looking at is even like a family of 2-dimensional Gaussians? If they're axis aligned, then axis aligned rectangles might do a good job of capturing discrepancy. But if you've got a really skew Gaussian that's arranged at a 45-degree angle, looking at partitions into axis aligned rectangles is going to do a terrible job. And so you might have to do something very complicated even in the D equals 2 case.
So in the original uniform testing, you have also some nice dependence on error probability, like a square root log 1 over delta. Do you also get these things here or no?
I don't think anyone has done work on high probability testing in this regime. So yeah, I mean, of course, you can always get delta error probability by doing delta log 1 over delta many repetitions. And presumably one could take the high probability technology from the discrete distribution case and try to make it work in this case, but I don't think anyone has gotten around to doing that yet.
Is there a particular challenge for doing that?
I don't think that there's a particular challenge, but then again, I mean, doing that in the discrete distribution case was not particularly easy. So, I mean, there will probably be technical challenges that crop up when you try and do it, but I don't know of any like specific obstacle that will make it like a hard problem.
All right, thanks.
So early on, you had this notion of having different intervals, like different granularity, basically.
Sure.
And I didn't quite catch that part, but it seems like you're trying several T's in parallel, and then there should be, at least in my mind, I feel like there should be some sort of a union bound over all those tests.
Right. Yeah.
How did you? But it didn't.
Right. Yeah. So with this AK identity tester, you do a whole bunch of tests at different scales of t, and you do have to be a little bit careful because you want to make sure that all of these tests return the correct answer. And so this means doing some kind of a union bound, which means that you can't have all of these tests working with a probability 1/3 of error. The thing that saves you here is that the tests with larger t's require fewer samples. And so you can afford to just run those tests multiple times to decrease the probability of error. So the t equals 1 tester, you'll only run once, but because as t gets larger, you start needing exponentially fewer samples, you can just run them more times. And so, the first tester has a 1/4 probability of failure, and the next one has a 1/8 probability of failure, and so on and so forth. And maybe you have to do slightly better than that to keep it bounded away from a half, but you get the idea.
Any final question? Okay, let's thank Daniel again.